Hi, everybody. We are going to do notes for sections 5.1 today. So I'm going to share my screen. The slides are posted, and there's a handout that's posted, which you can use or not use. It's up to you. So let me go like this. Alrighty, so here we are. This is the slides. I'm going to be going back and forth between the slides and my handout. So you need your notebook, and you need your periodic table, and your computer, obviously. And if you want the handout, you can print it off. If you don't want the handout, you can just write a few things down in your notebook. Okay. All right. So section 5.1, this is all about bonding. Okay. In other words, bonding is how atoms come together to form molecules. This whole topic is called bonding. So before we talk about bonding, I want you to review with yourself or your friend these questions. Okay, what is a valence electron? And then how many valence electrons are in aluminum, chlorine, and calcium? So you need your periodic table for this, and I'm going to write the answers down on the handout. Again, if you don't have the handout, you can just write them in your notebook, or else just think about it. Okay, so I'm going to switch over here to my paper. All right, a valence electron is an electron in the outermost energy level. Electron in the outermost energy level. So we're going back to talk about energy levels. I think this was unit 4 when we talked about the Bohr model and electron configurations and energy levels and so on and so forth. So we're going back to that kind of topic. Alrighty. And then the next review question was, how many electrons does calcium have? So to find valence electrons, you need your periodic table, and you need to count over from the left to whatever atom you're aiming for. So calcium is right here. So 1, 2. So calcium has 2 valence electrons. And or you can go up to the top of the column that calcium is in, and that too tells you how many valence electrons it's got. And the 2 plus is the charge, which we've talked about a lot. So calcium has 2 valence electrons. Aluminum has, here's aluminum right there. Go up to the top, it's got 3, or you can count over 1, 2, 3. Aluminum has 3, and chlorine is right there, and it's got 1, 2, 3, 4, 5, 6, 7. So chlorine has 7, and there's the 7 right there. All right, so 7 valence electrons for everything in this column, including chlorine. 7. Okay. All right. So now we're going to talk about bonding, because bonding is all about what is going on with these valence electrons. Okay. These valence electrons are really the most important electrons of all. All right. They're super awesome. Okay. So atoms bond because. So I'm going to go back over here to my slide and I'll write it on the paper, but we are on slide number 4. The first reason atoms bond is because they are more stable when their outer valence shell of electrons is full. And I will go back and write this down on the paper. But here's a picture of the Bohr model of sodium. So sodium has 11 protons and 11 electrons. And if we counted, we got 2 there on energy level 1. We have 8 on energy level 2. And we have 1 on energy level 3. So I'm just going to remind you on your periodic table how this works. So here's sodium. It's got 11 protons, and if it's neutral, it has 11 electrons. Okay, and the first row is energy level 1, so that's got 2 electrons. The second row is energy level 2, that's got 8 electrons. And for sodium, the third row, it's right there, that has only 1 more. So you might remember principal energy levels are N equals 1, N equals 2, N equals 3. And if I were going to do the electron configuration of sodium, I would go 1s2, 2s2, 2p6, 3s1. So for sodium, that's what it would be. And this electron right there, that one, is its one valence electron. It's got one valence electron. Okay, so reason that atoms bond number 1 is because they are more stable when they're bonded. They bond to become stable. Okay, the second reason is to fill their valence shell. Okay, and here's sodium again. So the valence energy level, or the valence shell, is this outermost shell, and there's only one right there, right? Sodium's got 11 electrons. 1 electron is in that outer shell for sodium. All right, and there's a new rule here. It takes 8 electrons in the outermost shell, outer energy level, to be considered full. So if atoms bond to fill their outer shell, full means that you have 8 electrons out there. Right now, sodium's only got 1. So sodium is very unstable like that. All right, the octet rule is just the rule that says atoms want 8 electrons in their valence shell. So says atoms want 8 electrons in their valence shell. All right, octet means 8. So octet rule means sodium is going to want to fill that. It would need 7 more to be full. That's one way it could do it, or it could lose that one. But we'll get to that in a second, okay? Exceptions to the octet rule are hydrogen and helium. They only need 2 electrons in their outermost shell, in outermost energy level. Ooh, my handwriting is not good. Energy level to be considered full, because they only have 1 energy level. Here's hydrogen, N equals 1. To have that energy level full, it would need 1 more. Helium is only on energy level 1. It's already got 2. So that's called the duet rule. A duet means 2. All right, so we're going to draw a whole bunch of compounds bonding. So we'll have to be reminded about this duet rule. Okay. All right. So let me go back to my slides here for a second. All righty. They bond to fill their outer shell. So sodium, like this, does not have a full valence shell. So it's going to bond with something else. And when that happens, they'll both get a full outer shell and they will both be stable. All right. That's the octet rule. Okay. 8 electrons in their valence shell. And then the exceptions are hydrogen and helium that can only hold 2 in their outermost energy level, which is energy level 1. That's called the duet rule. All right, so there's a recap for you. You can always go back to your slides on Schoology and fill that in if you want to. That's what I just said. All right, and then the question is, how does this happen, right? How does how do valence shells get full? There's 2 different ways. Depends on what kind of compound you have. If you have an ionic compound, it does it a certain way. If you have a covalent compound, it does it a different way. And as a reminder, covalent and molecular mean the same thing. So if we were in class, I would ask you to review this with your neighbor, but we're not. So let us go back to our paper and we'll write some of this in. We're going to do ionic bonding first. Okay, so in an ionic bond, the metal, let me back up. Ionic compounds are a metal plus a non-metal, okay? Or a polyatomic ion with a non-metal, but we're mostly going to be dealing with simple metals and non-metals. All right, and covalent is non-metal, non-metal. So depending on what kind of compound you have, their bonding is different. All right, so let's do ionic. All right, in an ionic bond, the metal atom gives its valence electrons to the non-metal atom, and electrons are transferred to form an ionic bond. All right, so let me write this down here for you on this paper if you're using it. An ionic bond forms between a metal. If you're not using the handout, you should definitely be writing this down in your notebook. All right, between a metal and a non-metal. And how that happens is that the metal gives its valence electrons, or its outermost electrons, to the non-metal. Oops, cheapers, non-metal. All right, so electrons are said to transfer. Electrons are transferred. Okay, so the non-metal takes the electron from the metal. So let me draw this out for you. Okay, these are the Bohr models with the rings. You know how much I like to draw these. Okay, so let's do sodium. It's got 11 electrons. So here's the first two in energy level 1. Energy level 2 has 8. 1, 2, 3, 4, 5, 6, 7, 8. Energy level 3 has 1. So that's a total of 11. Chlorine has 17 electrons. So here's 2. 1, 2, 3, 4, 5, 6, 7, 8. Energy level 3 for chlorine has 7. 2, 3, 4, 5, 6, 7. So let's just look at our periodic table and I'll show you. All right, here's sodium. Energy level 1 has 2. Energy level 2 has 8. Energy level 3 has 1. And then chlorine is a nonmetal. Energy level 1 has 2. Energy level 2 has 8. And energy level 3 has 7. So that's what I was drawing right there. Okay, so before they bond, that's what they look like. This one does not have a full valence level. And this one doesn't have a full valence electron. They both want to have 8. So what happens when ionic bonds form is that this metal gives its electron to the nonmetal. So the electron gets transferred over to that empty spot. Okay, so that metal loses an electron. The nonmetal gains an electron in this case. So I'm going to redraw this after they have bonded. Here's sodium again. All right, it's got 11 protons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now its third energy level is empty because it's given that electron to chlorine. Here's chlorine. Here's its first energy level, has 2. 1, 2, 3, 4, 5, 6, 7, 8. Now its third energy level had 7. But now it's got one extra one. 1, 2, 3, 4, 5, 6, 7, 8. All right, this one of these came from sodium. All right, so now sodium has 17 protons, but now it's got 18 electrons. So it is going to have a charge of -1. It's got one more electron than proton. Sodium has 11 protons, but now it's only got 10 electrons, so it's going to have a charge of +1. So this is why those charges that we've been working with are what they are, because 10 electrons and 11 protons give sodium a charge of +1. Chlorine is now chloride, so sodium is a +1, chlorine is a -1. Okay, so let's do a little recap here. All right, and this is all on the slides. I'm just going to write it down here. So I am on slide right there. There's those pictures that I drew. There's sodium's 1 valence electron. Chlorine has 7. After they've bonded, sodium doesn't have any in its third energy level. It's not even drawn on here. And chlorine now has a full valence shell. So sodium has a full valence shell because now energy level 2 is its outermost shell and it has 8. And chlorine has a full valence shell because now it has 8 in its valence shell. Alrighty, and that's just another picture. All right, let's write down this stuff on our notes on the handout or in your notebook. Okay, this is our summary. All right, I'm going back to my paper. All right, summary. Metals have low ionization energies. Ionization energies. Okay, so they give up electrons easily. All right, non-metals. Oh wait, metals lose electrons. Okay, non-metals gain electrons. All right, metals become positive cations. Non-metals have gained an electron. They become negative anions. All right, and the positive charge and the negative charge are attracted to each other, so they make a bond. So that is what an ionic bond is, okay? It's an attraction between the positive metal cation and the negative nonmetal anion. All right, awesome. Let us move on, okay? Let's talk about the other kind of bonding, which is covalent bonds. Okay, covalent bonding is very different than ionic bonding. All right, covalent compounds are between a non-metal and a non-metal. So their bonding is different. When two non-metals bond, there's no ions. These are the ones where you would name using those prefixes and you didn't have to balance the charges. It was so much easier. All right, so we don't have to deal with ions and they don't transfer their electrons, they share electrons. Okay, so non-metal plus non-metal elements will form a covalent bond. Two non-metals will bond to form a covalent compound. All right, and electrons are shared. All right, we still have the octet rule. Okay, the octet rule still has to be obeyed. Still obey the octet rule. But they fill valence shells by sharing electrons, not transferring electrons. Okay, and we're going to go much more further into this later. Okay, there's two kinds of covalent bonds. The first one's called non-polar. Okay, they share electrons evenly. In other words, here's a little picture. If you can see it, I'll show you the slide. All right, those two atoms are bonded and their bond is made by those electrons being shared and they're pulling on them with equal strength. So that bond is basically right in the middle of those two atoms and they're said to be sharing those electrons evenly. That's non-polar. All right, polar covalent, all right, do not, atoms in a polar covalent bond do not share the electrons evenly. So here's a little picture of that. Here's a Cl bonded to an H, all right, and the bond, the electrons are way down there that are being shared way closer to that chlorine than that H. That chlorine is pulling harder on the electrons than the H is. So we end up with the electrons down by the chlorine more than by the H. Okay, that's said to be not sharing evenly. All right, so they're polar. So this end becomes a little bit negative and this end becomes a little bit positive, you know, kind of like a battery has a negative end and a positive end. That's why it's called polar, because we have poles, positive sides and negative sides. All righty, let's go back to the slides here for a second. All right, so covalent bonds share their electrons. Non-polar covalent bonds share the electrons evenly. Polar covalent bonds share them unevenly. And that's the same picture, okay? And the next question is, how do we know if they're being shared equally or not? And we come back to this question in the next unit, actually. Okay, so let's finish this up and talk about metal bonding. Metals is the last kind of bonding. This is all printed out on this handout. So either write it down or get the handout, okay? They form between metal atoms, so two metals, sodium and sodium, you know, copper and copper, okay? The thing that's different is that the electrons move freely throughout the structure like a sea of electrons. They aren't bonded specifically to other atoms, but they kind of get shared in the piece of metal. So if I had a piece of metal, let me go back to my paper. If I had a piece of metal, let's say I have a piece of copper or something, the electrons of all the copper atoms in there are just floating around, okay? And that's why sometimes metals can be magnetized. If all the electrons get pulled to one end, we'd have a negative piece of metal, negative end, like this would be like a magnet, okay? And then the other end would be left more positive, all right? But in other words, all you really need to know for metals is that these electrons are free floating, and it's called a sea of electrons. All right, okay, we're almost done. All right, this little table is super important because different properties of substances depend upon what kind of bonding they have. So again, either make this table in your notebook, okay, or somehow get it written down because you definitely need to know these things, okay? So these are all on the slides about how bonding affects properties, the type of bonding, okay? There'll be some exceptions, but the pattern holds pretty true. All right, and I'm just gonna fill this in on my paper, and then you can fill it in or not fill it in, okay? Write it down. You do need to know it. And we're going to do a lab about this. Okay, so solubility in water means, this should say solid. Does it dissolve in water? Okay, ionic compounds definitely dissolve pretty well in water for the most part. So I'm going to say yes. And remember, ionic is a metal plus a non-metal. Okay. Uh, Covalent, polar covalent things do tend to dissolve in water. Okay, and I'll do a little demo for this. Non-polar covalent do not dissolve in water. And metals, metals don't dissolve in water. You can't put a piece of metal in water and have it dissolve. All right, conductivity. Okay, if I have a dissolved ionic compound, so for example, salt water, that will conduct a current because we need ions to get a current. All right, electricity is just a moving charge. So if you have floating ions, here, I'll draw you a little picture because why not? If I have salt water with all these little ions floating around, positive and negative ions, I can make a current happen. I could light up a light bulb if I stuck a thing in there, which I'll demonstrate for you. Okay, and you're actually going to do that in the lab, I think. Polar covalent molecules do not conduct a current ever. Any kind of covalent never conducts a current. Okay, because there's no ions. You got to have ions if you're going to get a current, an electrical current. Okay, so covalent, no matter what kind of covalent it is, isn't going to give you a current. Okay, metals, don't dissolve, so they're not going to give you a current if they're dissolved. Well, they don't dissolve, so that's pretty much not relevant. Okay. All right. If they're solid, if you take salt, like solid salt, it is not going to give you a current because there's no ions. Okay. No ions if it's solid. Okay. Solid covalent, any kind of covalent is not going to give you a current. Solid metal will conduct a current, right? Metals are, you can make them electrical, right? They can make a current flow through them. All right, and then melting points and boiling points. Okay, ionic compounds have the highest melting point and boiling points because those charges are held together tightly. The positive and negative charges are held tightly together. So you have to add a lot of energy to make it melt or boil. Okay, polar covalent have the middle. Their melting points aren't quite as high as ionic, but they're higher than the non-polar covalent, which has the lowest melting points and boiling points, and metals, the melting points and boiling points vary. Okay, so I'm going to quit sharing my screen. Hope that helped. Bring your questions to class and see you soon, I hope.